And now it's just conversion.
That's how I felt.
It's just, when I was a student, I knew I hated waiting to get my test back. And so, why should you guys have to wait? If I can keep you from waiting. Yeah, I don't do fractions of points. That's what it is. Like, it's a 7-point question. All right, 7. You started right, math error 5. You didn't start right, but with your bad math, you got a reasonable answer. 3. All wrong. 0. Done. So, I could have probably debated longer about where'd you go wrong with your math? Should I give you a fraction point for this, that, and it all works out. All right. So, thin crowd today. Thin crowd. Okay. Wait, Melissa.
I have a question. For the math read, we had one due on Friday.
I moved it to Monday. Yep. So the math string, no homework this week. How about that?
What?
Yeah, no homework this week. Because I try to avoid Friday homeworks because I know probably Friday nights you may be doing something else. Yeah, you may be doing something else other than homework. So it's going to be Monday and Wednesday of next week. We'll do a group quiz next Monday. I got your exams back. And we got some new stuff to cover. We're not leaving K's in the dust. We're just going to talk about K's in terms of free energy and thermodynamics. So let's see here. All right. So you will not need a calculator for the lecture today. Today is just a bunch of definitions and just discussion. So calculator-free morning. You're not supposed to cheer that. No cheering. It's like, oh, we can't calculate. It's going to be just a bunch of terms and definitions. I know, sad. Okay. So, free energy and thermodynamics, chapter 17. All right, so some of this stuff you are familiar with from other classes or maybe 108, depending on how recently you took it. Right, so there is this thing called spontaneous change. And we're going to talk about spontaneous change and how it relates to equilibrium. So there's two kinds of change, right? There's chemical changes, there's physical changes. A chemical change is where you do a reaction where the products are different than the reactants. All right, so pretty much when you think of chemistry, this is what you're thinking of, right? You put in something and you get out something else. All right, that's a chemical change. You have your physical changes. That usually changes the states of matter. Or it could be a physical change is that the volume changed, the pressure changed, or you went from solid to liquid, liquid to gas. You precipitated, which would be right, that's aqueous to solid. All right, so those are your chemical, physical changes, right? We can talk about how these changes happen. We'll use the word spontaneous to indicate that the change has occurred without outside intervention. So you have not done something to the reaction, but it has changed. Spontaneous does not imply speedy. So when we use spontaneous in English, right, you think of instantaneous, right? If it's a spontaneous moment, you decide on the fly that you're going to go drive to Vegas, right? That's a spontaneous decision. It'd be a long drive. But that's not true in chemistry. Spontaneous just tells us that we are headed towards equilibrium. You are, like your cells are spontaneously dying, right? But your cells don't all die at once. They're all on the process of dying. Well, I suppose when you actually die. But, right, you're moving towards a system of equilibrium, right? All your cells are moving there. It doesn't tell you how fast that's going to happen. It just says it is happening. So, up to this point, we've been discussing product favored reactions or reactant favored reactions. But we're going to look at not just are they favored one direction or the other, but we are going to determine how they get to equilibrium and how we can influence that. So we're going to add in how does the reaction get to equilibrium and how we can influence that. So we're going to combine Le Chatelier's, right, which tells us if we do this to the system, it goes this way or comes back. We're going to combine that with heat, entropy, and Gibbs free energy. Yay! You'll be excited later. If you're not excited yet, it's coming. Excitement. Yeah. Woohoo! All right. Let's look at heat and spontaneity. All right, so heat, right? We covered this whenever you took 108s, right? Heat is our delta H. It's our enthalpy. All right, so let's take a look at these. I have 5 examples. So let's talk about these 5 examples and how heat and spontaneity work together. So let's take a look at, this is a good review question. So what is this guy over here? It's a strong acid, right, reacting with a strong base to make our salt and water. What do we know about the delta H of that? It is negative. Yep. And if it's negative, what does that tell us about its likelihood of going forward based on what you know now? Spontaneous, right? We know that when we mix a strong acid, strong acid and strong base, we get our salt and water. If you've never done that, take 2 seconds in lab next time. Don't let your TA see you because you're not supposed to do this. But pour together some strong acid, strong base, and the beaker gets super, super, super hot. Really, really hot. Don't do that because it's really not, you're not supposed to do that. But just a little bit. If you pour a little bit together. Or come up to my lab and we can do it in my lab and I'll know what you're doing. So we can try that out. All right, so negative, spontaneous. All right, what if I got my methane, my oxygen making carbon dioxide and water. What do we usually call that reaction when I make carbon dioxide and water? Right, combustion. Got a combustion reaction going on here. What do we know about the heat released for a combustion reaction? Right, hopefully, based on what you know about fire. Fire is hot, which means the delta H is negative, which means this should also be spontaneous. All right, here's my trick one. Ammonium nitrate, when it dissolves into water, is actually endothermic. It actually gets colder. So if it gets colder, what does it tell you about the sign of delta H? Positive. But it's still spontaneous, right? Because you have a solid dissolving. So that should still be spontaneous. Here are my other two trick questions. I have a gas in this crazy setup, right? I have one gas on one side. I open up the stopcock and let it flow whichever way it wants to go, right? It's going to fill up both sides. Has heat been released or needed to do that? No, right? I just opened it. I didn't heat it. I didn't cool it. Nothing crazy. So what's the delta H of that? The delta H is 0. But was it spontaneous? Yeah. This would seem to indicate we need more information to be able to predict spontaneousness, which I'm going to give you. I'm leading up to, delta H is a good predictor. It's not the best predictor. There's some other factors in there that help us predict what's actually spontaneous. All right, let's think about melting ice, which today's a good day to do it because it's freezing outside. So if we think about melting ice, is that a chemical change or a physical change? Okay, physical change. When you melt ice, do you need to add heat to melt it, or does melting release heat? When you think about ice cube, you should add heat. So if I add heat, is it endo or exo? Endo, so delta H is positive. And spontaneous. But is it spontaneous at all temperatures? No, right? If I imagine we went to Antarctica with my blow dryer and was like working on a glacier, right? While I'm adding heat to the system, is it melting? Not really, because it's so cold that the amount of heat I'm adding is not causing it to melt. But if I put my ice cube in summer in Georgia, right, it's hot enough now that it is going to be spontaneous. Not spontaneous at all temperatures. You think about the opposite too. You think about freezing ice, right? That ice will definitely freeze at certain temperatures, but not other temperatures. So it's spontaneous some of the time, but not all the time. So there must be more to this. Oop, that's not right. Describe, how do you spell it? The B maybe? Describe? There we go. Everyone get that spont is spontaneous? I always misspell it, so I just shorthanded it. Spontaneous. So, how do we know if a reaction is spontaneous if delta H is not enough to tell us? Let's talk about some entropy. So entropy is given the symbol S and is the second law of thermodynamics, where we talk about in a spontaneous process, which means the process moving towards equilibrium, the entropy of the universe increases, which is a big statement. I mean, if you really think about it, that I'm saying that what I'm doing here on my bench is affecting the entropy of the known universe. I know, it's pretty mind-blowing, pretty crazy. So we're gonna bring it down a little bit. We'll talk about smaller scale, and eventually I'll blow your mind later. We'll work on the whole universe. Although, I mean, honestly, taking a lecture with here every day should be like, wow, that's amazing. I want to take more chemistry. Oh, okay. Maybe not. Maybe not. All right. All right, here I have my delta S, which means change in entropy, final minus initial. If it's just final minus initial, what kind of function is that? Right, we got ourselves a state function right here. All right, so we have a state function, which means only dependent on initial and final states. So the second law is built around the idea that spontaneous change results in increased energy dispersal. So we're saying for delta S, right, this change in entropy to be positive, my final state must have more entropy than my initial state, right, because this is subtraction. So why is that the second law? Well, let's take a look at a very small scale experiment and see if we can kind of make some predictions about bigger scale experiments. So let's say we have this experiment. So I have the dispersal of energy over many different energy states, and that's going to be the key to entropy. Key. Look at that, key. I would star that statement. It'll probably come up on a multiple choice question someplace. Hint, hint. Just saying. If I was going to write a test, I'd probably put that on there. It's a pretty genius statement. All right, so let's say I have my two systems here. I have my hot system, as in temperature hot, not as in it looks hot. All right, temperature-wise. Look at that. I color-coded it. It's now red. That's how you know it's hot. All right, what are the big zigzaggy arrows telling you in my cartoon? Yeah, what do we know about hot systems and their amount of energy? Right? They have a lot more energy. Hot things have more energy. Right? So that's what the arrows are showing me. They have a lot more energy and they're bouncing everywhere. All right, what's going on over here in my cold reaction? Do I have any arrows? No. What does that tell you about the motion of those molecules? None, right? There's not really. So this is my ice cube, right? That's my solid. This is my, I decided my coffee is too hot. Right, so this is my coffee. I don't know why you do this, that'd be disgusting. But here's my ice cube I'm going to put into my coffee. What happens to the temperature of the coffee? What happens to the temperature of my ice cube? Goes up, right? Because I put these two, I don't have a color in between red and I don't have purple, so I'm going to call it green. I know it doesn't work with the color wheel. I'm sorry. So I put these two systems together and the thermal energy has been transferred. This gave some energy to that. The thermal energy has been transferred in both directions. And now the system has a distribution of energies. Right, so you think about like in numbers, if that's easier, like this is all 100, this is all 0, so what's the average between a set of 100 and a set of 0? 50, right? So now everybody has 50. Or it could be temperature. I got hot and cold, now everybody's just warm. So instead of having everybody having two chimney stacks of numbers, I have more like a Gaussian distribution. Who's taking statistics? Oh, excellent, because we're about to venture into some statistics areas. A little Gaussians. Oh, I'm not ready for that yet. Sorry. I got more fun facts to write down before we're ready. All right, so we can also look at an energy distribution in a system. Now, obviously, how many atoms are in a mole? A lot, right? So I'm not going to look at a whole mole of molecules yet. I'm going to start with, I think I start off with 4. 4 atoms, right? Because we can make good predictions using just 4 or 5, and then we'll extrapolate out to a whole mole of atoms, only because it'll take me forever to draw that many little dots to represent it. So we're just going to do small scale. So let's say I have a system with just 4 atoms in it. I give 2 of the atoms some amount of energy, and 2 atoms I give no energy to. This is the picture that's on the next slide. Right, here I have, they're color-coded. Number 3 and number 4 have energy. Number 1 and 2 have no energy. Using our knowledge of statistics, we can draw 10 different ways to redistribute that energy. Right, so I could put both energies on 1 and everyone else has 0. I could put energy on 1 and 2 and nothing on 3 and 4. I could put energy on 1 and 3 and nothing on 2 and 4. I could put the energy on 1, 4, right? You can keep coming up with different ways to combination that energy. Looking at my picture, how many different ways have the energy only on 1 atom? So a double circle around 1 atom. 4. So only 4 of the 10 ways to arrange this system. All right, so I have 4 ways out of 10 that have it only on 1 atom. I have 6 out of 10 that have it on 2 atoms. So what would you say is true if I had a mole of atoms? Would most of the atoms have an arrangement where it's only on 1 atom, or would most of the arrangements have it distributed amongst the atoms? Right, it should be distributed based on my little tiny system. Less than half the time, 1 atom has all the energy. That's true for a larger system. For example, a mole. So with a larger system, we expect to see the energy distributed amongst several atoms, not just one atom. All right, so what if I now have the same number of atoms but more energy? So before I had either 0 energy or 1 energy. Now I have 3 versus 0. So I have 2 particles with 3 packets of energy, quanta of energy, and I got 2 particles with no energy. I can come up with, I think it's 64 different ways to arrange this. Because I have more energy to put more places. So I can imagine a combination where 3 of them have none and 1 has all of it. I can come up with a combination where 1 has none, 3 have some, 2 and 2, 2, 2 and 4, right? All these different options of different ways to arrange it. So there's only 2 ways to arrange the atoms where all, I guess not 2, I went 4, sorry, 4. There's only 4 ways to arrange it so that only 1 atom has energy. So is that a small percentage of how many different ways I could arrange it? I was wrong. It's actually 70, I think 72, maybe 96 ways. Anyway, right, very small percentage of ways that only 1 atom has all the energy. It is much more likely that all the atoms have some combination of energy. So as the number of atoms and number, I guess, amount of energy, rather than number of energy levels. There'll be some more likely ways to arrange the energy. All right, look at my little diagram up here. This one's the most likely way to arrange it. I have 24 different ways I could put 1 with 0, 1 with 1, 2 with 2, 1 with 3. That's the most likely way to arrange it. This guy over here and this guy over here, I guess there are 3 least likely ways to arrange it because they only have 4 different ways I could put it. So that's kind of the idea behind entropy. There's going to be more likely ways to arrange your energy than other ways. And so we'll make some predictions about what's the most likely way to arrange our energy. What's the least likely way to arrange our energy? All right, so it's difficult to calculate exact energy amounts. All right, we can't make good predictions about 1 atom has 1 quanta, 1 atom has blah, blah. So we're going to look at the dispersal of matter among the system rather than energy and do a similar experiment to what I just had on that paper. So let's say, hopefully everyone has their drawing skills out today because we're going to do some amazing drawings. Okay. Let's look at We're going to draw that same gas cylinder thing I had. It had two bulbs and one thing in the center. So let's say I have this. Whew. Good. So far, so good. Okay, it's closed. And on one side of my little container, I have a triangle and a square. I'm going to open up that. I'm going to give everybody a minute. How many different combinations of places can that square and triangle be? It'll be 4. So go ahead and figure out if you can draw all 4 different ways to put those triangles and squares places. Everybody get something amazingly sketchable like that? Good, good, good. All right, so what is the probability that the square and triangle stay where they were? 1 in 4, right? 25% probability that they'll stay where they are. What's the probability that they both moved to the other side? Also 25%. What's the probability that they split the difference? 50%, right? So these are pretty much equivalent in terms of what they look like. So 25% or 1/4 probability that they stay. 1/4 probability both move. And 1/2 probability one moves. Good there, everyone feel confident in the fractions? Right, ready to take up one level of challenge? We're going to put a third molecule in there. So now I have this guy over here. I got, oh, that's not it. I have this. Just kidding, that was not what I had. I have a triangle and a square. And what's a good third shape? Heart, okay. Okay, it's closed. Okay, how many different ways can I arrange this now? Not 3 to the third. There's only 2 places it could be. 2 cubed. 2 cubed. So here, right, I had 2 molecules with 2 places to go. So that's 2 squared. Now I have 3 molecules with 2 places to go, so it's 2 cubed. So 2 cubed is 8. So go ahead and draw 8 flasks and figure out all different 8 ways we can. I'm not going to do anything trickier than this because then it takes forever to draw. We'll use math for the rest of them. Yay, math. Oh, my flasks are looking bad. Not good flasks. I would not sell anyone a flask that looks like this. It's not even closed. Okay, let's see here. Something like that. Let's see if that's all right. 2. Okay, not pretty. All right, looking at our figures and based on your stellar knowledge of probability and statistics, what is the probability that the molecules did not move? 1/8, right? What's the probability that everybody moved? So is it likely that they would either all stay or all move? It is not the most likely scenario, right? It is more likely, 6 out of 8, that somebody will move, right? Because we have all the other choices. So let's use some math, some quick mental math. I'll flip it on the other side because it's still undecided.
Yeah.
Just I ran out of space. We'll go slow. Let's say we have 10 molecules. If I have 10 molecules, how many different flasks would I have to draw? 2 raised to the power of 2 to the 10th, which happens to be 1,024 different flasks I would have to draw. What's the probability that the molecules would all stay in one flask? Okay. What's the probability that they would all move? How likely are those two compared to some distribution of energy? Not likely, right? All right. We're getting close to a mole. Okay, let's say now I have 20 molecules. It'll be 2 to the 20th, which happens to be 1, 0, 4, 8, 5, 7, 6. Different flasks I would have to draw. What's the probability that all the molecules would stay put? Pretty much 0 at this point, but we'll say 1 out of, what is that, 1,048,576 chance of it staying put. Right, and then to the 6, so it's small. Okay, how many molecules are in a mole? Okay. If you had your calculator out, I would have you put it in there. Turns out your calculator will just give you the word error. Because it's such a large number, your calculator can't handle it. So it is practically infinity. So then what does this fraction turn out to be? 0. So it's telling you mathematically and or sketching wise the likelihood of the molecules all staying put, 0. Likelihood of all the molecules moving, 0. Likelihood of some combination of energy distribution, 1. Right, because if you're not 0, then you're 1. So energy distribution is the way that our systems are going to work. So we're going to talk about entropy in terms of how do we determine what the distribution should be. Let's see. So imagine you're looking at this flask again over here, my little flask, just this guy right here. Looking at my flask with just 2 molecules in one flask. The entropy of the state, which is the energy distribution.
The entropy
Increases
with the number of
energetically
equivalent ways
to arrange the components. Right, so here I had
4 ways to do it.
Here I had 8 ways.
Then I
I
had
had 1,000 ways.
ways. Then I had
A million ways.
then I had
An infinite number
of ways
to arrange it. So the entropy,
increased with
the number of ways
to
arrange the system,
which means that the
state
with the
highest entropy
will have the greatest
greatest dispersal of
energy. So
In our case, it would be
the state
state that had the most
particles in the most volume. So entropy is looking to
disperse the energy
in as many places
as it possibly can.
doesn't want to keep it all
On
on
one side of the flask,
doesn't want to keep it all on the other side of the flask
wants to keep it
in some combination between the two.
now, obviously
Obviously, our systems are
more complicated
complicated than just a 50-50
chance of which side they end up.
up on. So the second law states that
For any spontaneous process,
right, the
entropy of the universe
increases right, so delta S of the universe
has to be greater than
0 if the spontaneous
if the process is spontaneous.
right,
So if we have S final,
final minus S initial. If I want delta S
S to be greater than
0,
which one has
has to be the larger component,
the final or the initial?
right?
For that to be true,
True, the final has to be greater than the initial,
otherwise you end up with a
number less than 0.
So the second law
It's there because it
explains all these phenomena
phenomenons that we see that doesn't make sense if
if we only had the
first law of thermodynamics.
which one is the first law? Right.
Energy's not created, right, you can't gain, lose,
Lose energy, energy's all
equal, all, everywhere, nobody's creating,
destroying it, smashing it. No.
nobody's doing any of that. It's just moving.
So,
So let's take a look at that ice cube in water
water
again.
again.
So we talked about the fact that
The ice cube in the water, right,
right, the ice cube is going
to
right, well, I guess let's start with this. We'll start with this.
right, I think everybody would agree with this,
That's right. Heat travels high temperature to low.
low temperature.
If we
Only had the first law. I have my ice cube, right, which
which is the cold thing,
so it's going to would lose
all right, so the heat's traveling high temperature to low temperature.
temperature. The
Ice cube, because it's traveling that way, the ice cube would lose
lose energy and the heat
would the water would gain the energy. But if it's lost energy, it would seemingly, the ice cube would get colder and your water would get hotter. Which you know doesn't make any sense. That'd be crazy. If you put an ice cube in there, and you pulled the ice cube out and it was colder than when it started, and your water went from like room temperature to boiling because you put an ice cube in it. That doesn't work, right? That's craziness. That's like science fiction. That'd be a great story, though. What if the second law didn't exist and you had a world based on the only first law of thermodynamics? May not do well in the movie theaters. But it'd be interesting. Okay, it's clearly not true. All right, so we need the second law. So my final 2 minutes, I'll explain why. So like we had in that figure before, right, where we had the two boxes coming together and one had energy and one didn't, and they come together. Second law says that the energy has to be dispersed, right? And the hot water had a lot of energy, and the cold ice cube had no energy. So that transfer energy from the water to the ice to make the ice warmer and the water colder results in energy dispersal. I've now put energy in more locations because the energy was all concentrated in the warm water and there was no energy in the ice cube. So now I've taken some of that warm water energy, put it in the ice cube. So now I have more places to put that energy, so the energy distribution has gone up. The universe is happy because I have dispersed the energy, because the energy of the entropy of the universe has now also increased. So next time you put your ice cube in your water, be like, entropy of the universe is currently increasing. Right there, right there. You should probably shout that. And everybody be like, whoa, that's exciting. Or they'll be like, man, they need to lay off the studying. All right, we will pick this up on Friday and talk about changes in state and other fascinating facts of entropy.